Hello and welcome from our side to today's webinar. My name is Stefan Meyer. I'm working as an R&D engineer in the location-based services lab of Schwarz. And together with my colleague Adrian, we're going to present you today's topic, which is high-accuracy GNSS in 5G, RTK-PPP and RTK-PPP. Let me give you a quick overview about the agenda. The webinar is separated into three parts. The first part is high-accuracy GNSS, the basics, which will be presented by myself. The second part is a market outlook for high-accuracy GNSS by Adrian. And the third part is also presented by Adrian, antenna testing for high-accuracy GNSS. Let me start with the basics of part one. What is high-accuracy GNSS and how is it different from standard accuracy GNSS? Well, fundamentally, both are working on the same signals. We have a carrier wave in GPS L1, it's the 1.5 gigahertz approximately, and on that carrier wave there is a modulated ranging code, a PRN code, pseudo-random noise code, and that ranging code is used by standard accuracy receivers to determine the distance between the receiver and the satellite. The PRN code is repeating itself only every 300 kilometers for GPS L1CA, and the individual chips are approximately 300 meters. So when you compare that to the accuracy of standard accuracy GNSS, which is around a few meters, we see that a receiver can locate itself with a certain percentage, let's say 1 to 10% of the ranging code. And this is actually a fundamental boundary because there is code noise, etc. So it's not actually easy to push that limit further based on code-based GNSS. Now the trick about high-accuracy GNSS is that it's not using the code, the PRN code, but it's using the carrier wave itself. And the carrier wave has a much shorter wavelength of only 20 centimeters for GPS L1CA. That means if we locate ourselves with 10% accuracy within those 20 centimeters, we end up at 2 centimeters, which is actually an accuracy that is perfectly possible with those techniques. And this is the fundamental trick. We move from the code to the carrier, and then we end up with a much higher accuracy because we use a finer scale. Now, there is actually a catch, and that is that the carrier is a sine wave. The sine wave, one sine wave looks like the other, so it's repeating itself every 20 centimeters. So we know precisely where we are within those 20 centimeters, but we do not know how many chunks of 20 centimeters are between us and the satellite. And this is the so-called ambiguity that we have to sort out to find a high accuracy fix. Remember, for the code-based positioning, the repetition was only every 300 kilometers, so it's much easier to sort out that ambiguity. Now let's look at the ambiguity resolution and a simple model, how it's working to understand better what are the challenges and limitations of high accuracy GNSS. To sort out the ambiguity, we start with a standard accuracy fix, and that is possible based on the code. So we know we are somewhere within that gray circle that you see here. That circle has approximately a diameter of several meters. And within that circle, we additionally know from the carrier measurement that we're from satellite 3 on one of the green lines. And those green lines are repeating every 20 centimeters. So we are one of those green lines. And if we take multiple satellites, we also know that we are on one of the yellow lines and one of the blue lines. And when you look at this pattern, you can see that those lines are intersecting on some points precisely, and on some points they're intersecting less precisely. So those points are called the candidates. And by observing those candidates, we can actually figure out which of those candidates is the true one, where we are really located. And once we have figured that out, we solve the ambiguities and we know precisely where we are with an accuracy of a few centimeters. Now, how can we observe those candidates? We can do so by either taking a longer time, looking at those points over time, or by using more satellites, or by using multiple frequencies. So if we have a different frequency, we have a different separation, the wavelength is different, and we can generate a calculatory frequency, and in the end we have less intersecting points and we can figure out more easily where we are. So long story short, the more satellites we have, the more frequencies we have, the faster the ambiguity resolution can work. Now what I told you here is nothing new. This is actually known since at least the late 1990s, and it's used since that time for high-end equipment. Now you may ask yourself, why don't we all use it now today? It's been 20 years, so why didn't it move its way to consumer equipment? And this has to do with several of those challenges that come along with ambiguity resolution and high accuracy GNSS. One thing is, that I didn't mention so far, that you need a continuous correction data stream. Before you can actually solve the ambiguities, you have to remove the errors as much as possible. And for that sake, you have to provide a continuous correction data stream to the receiver that you want to locate. And when you think about, let's say, 11 years back in 2010, data plans were still pretty expensive. You still had to pay a lot of money for a mobile data plan, and the correction data services themselves were also rather expensive because they were only intended for a small user base, like surveyors, scientists. So they had to share the cost. So getting correction data was a rather expensive task. Furthermore, of course, ambiguity resolution is a computational complex task, especially if you want to use advanced algorithms. And 10 years back, the mobile processors were simply not that fast as they are today. Above all, the number of GNSS constellations in 2010 was still rather limited. We only had one global constellation, GPS, and that GPS constellation was mostly providing only a single civil signal. And that makes it rather hard to sort out the ambiguities. Clever people came up with an idea how to use the military GPS signal without knowing the military code. This is the so-called codeless approach, and high-end receivers were able to use that. But it was a complex task and especially an expensive task. Now, more GNSS constellations were coming, and we will see on the next page how that changed the whole ambiguity resolution process. Furthermore, please keep in mind that a high accuracy ambiguity resolution is only valid if we are continuously observing the satellites. So as soon as we are driving under a bridge, we will lose the ambiguity resolution if we don't have additional precautions, and we have to reconverge. And if this convergence process or ambiguity resolution process takes several minutes, this high accuracy GNSS application would not be suitable for dynamic applications like usage in a car, for example. Last but not least, it's also about the antennas. High accuracy GNSS relies on good antennas, and those good and calibrated antennas were rather expensive as long as they were produced in low numbers for specialized equipment. So in a nutshell, high accuracy GNSS in 2010 was possible, of course, but it was more a niche market for high-end applications like surveying, science, and expensive receivers and correction data services were required. Now let's fast forward 11 years. How does the situation look right now? So let's look at each of those points and check out. For example, the continuous correction data stream is much less of a problem because we have all mobile internet connections virtually everywhere, and this is no problem anymore. Furthermore, also the correction data providers are now aiming for a mass market, so the costs per user are going down. The computational complexity is also less of a problem because we've got really capable mobile processors that we can actually use in the receivers. But probably the most important aspect is the number of GNSS constellations that is available today. Today we've got 4 global constellations and 2 regional constellations, GPS, GLONASS, Galileo, Beidou, and the regional QZSS and NAVIC. So all those constellations bring us simply more satellites, which is speeding up the process. But importantly, all the constellations are now also broadcasting multiple civil signals. So at least 2 civil signals. Some constellations even broadcast 3 or more civil signals. That means we can get the ambiguity resolution much, much faster than was possible in the past. And those signals are rather easy to use. It's not like this tricky process where you have to decode the military signal without the key. And this leads to a faster convergence time. Also, advancements in the Ssr, which is the correction data formats, have brought us faster convergence times. And there's also now accelerometers and gyroscopes in many receivers, which can actually bridge the gap while we are driving under an underpass. So we don't lose the ambiguity fix anymore. We can keep it for several seconds or even minutes. And last but not least, the calibrated antennas are now going down in prices and they're becoming more affordable. The higher number are produced of them. That leads to the fact that I'm proclaiming the golden age of GNSS is actually now. We are in a really good time for GNSS. There are many GNSS constellations, and this means that GNSS with high accuracy is coming into the mass market now, and the GNSS revolution is happening right now. Let's take a look at the correction data and the path how this correction data can be brought to the receiver. The most straightforward approach is actually by bringing it via the cellular mobile internet connection. This is called here top IP, unicast connection. So every user gets its own correction data stream. And yeah, this is actually a pretty straightforward and heavily used concept. Then there are new GNSS constellations that are also bringing high accuracy correction data directly from the satellites in the navigation message of the GNSS signals. For example, QZSS L6 signal, but also the upcoming Galileo high accuracy service are of that type. Then there are private companies that are renting transponders from commercial communication satellites and providing correction data from those satellites. And last but not least, the most recent variant is that mobile networks, LTE and 5G networks, can actually broadcast correction data. So not every user gets its own stream of correction data, but all the users in a cell can get a single stream of correction data. But we will take a look at that in more detail later. Fundamentally, there are two classes of correction data, OSR and SSR. They are also known under the term RTK and PPP. OSR is called observation space representation. So it works by the fact that a reference station is observing the satellite signal and transmitting those observations to the receiver. The receiver can do things like double differencing and remove error sources based on that correction data stream. This is kind of the classic approach that is used and supported by many receivers. And recently, there is another class gaining a lot of popularity, and that is state space representation, SSR. This SSR mode works by modeling the individual error components. So we're not simply transmitting our observations, but we are trying to make get some idea out of those observations and model the individual error components, like the satellite code and carrier bias, the satellite clock error, the orbit error, and the regional ionospheric and tropospheric errors. So in SSR mode, we are simply transmitting the parameters of error models to the receiver, which is bandwidth efficient and has several other advantages. It is also noteworthy to see that you can convert SSR mode in the receiver to OSR mode. So there are algorithms for that, so that is easily possible. The other direction is rather hard. Actually, converting OSR observations into SSR mode is a rather complex task that specialized companies are doing and typically not done in a receiver. Now, those are a lot of acronyms. Let me put some light on those acronyms. RTK, PPP, OSR, SSR. How do they actually relate to each other? RTK, Real-Time Kinematics, is probably the most popular OSR application. It's a differential positioning technique where observations from the reference stations are double differenced against the observations of the moving receiver. And it has a lot of merits. It's widely supported, and it's leading to fast convergence time and has good accuracies. However, it suffers from the fact that you need rather short baselines. So ideally less than 20 kilometers, probably less than 50 is also okay. But you need to be somewhere close to a reference station. And this is kind of limiting the application of RTK, and people are looking for other ways. Furthermore, you may need handovers if you drive from one reference station to the other, if you have a dynamic application. And this all leads to a rather regional coverage and some hurdles that RTK is posing for us. Another mode, PPP, is kind of a simple SSR mode. We are modeling only a sum of those error sources that I mentioned before, like the clock error or the orbit error, but not the ionospheric or tropospheric errors. And that means the correction data is valid on a worldwide basis. So we have a few monitoring stations, not that many as in RTK, and we can provide correction data for the whole Earth. And that has advantages, for example, if you want to find our precise location in the middle of an ocean or on an offshore wind platform, for example. However, the price to pay here is the longer convergence time. So it takes several minutes until we get a precise fix in PPP mode. And finally, in RTK-PPP, this is kind of tackled because RTK-PPP was trying to address the shortcomings of PPP and RTK and find out a new way how to get a composed system that offers the benefits of both. RTK-PPP is using correction for ionosphere and troposphere, and that leads to the fact that we have a very short convergence time, comparable almost to RTK, but we still need only very few reference stations, so we can still use RTK-PPP further away from that monitoring network. So it's promising to combine the strength of RTK and PPP. Why do we need those regional corrections? Why they are so important? The point is, for a fast convergence time, we have to sort out those regional natural effects that are impacting our signals. One of those effects is coming from the troposphere. This is combined or related to the water vapor density. So if you think of a cloud, the signal obviously is traveling at a different speed in a rainy cloud than it's in a clear sky. And this is actually why we need regional corrections for troposphere. And similarly, the ionospheric impacts, which are not driven by the regular weather as we know it, but more by the space weather, which is depending on the solar activity. And the ionospheric impact is also required to be modeled on a regional basis to achieve a fast and high accuracy. Well, let me focus on the Ssr standards because OSR is pretty well known and widespread. But in Ssr, since it's rather new, there are many different Ssr standards competing at the moment or are used also in different applications. So I call those Ssr standards here languages. We have Lpp, Spartan, RTCM, IGS, QCSS, L6, etc., etc. So that means they all have a similar content, but we have a lot of different encodings, like on those antique plates where we can see probably the same content, but not the same encoding. So that means if you want to build a receiver that is working on a worldwide basis, that receiver may need to support more than one language. It has to be rather polyglot, and that is at the moment a bit of a challenge because you have to spend additional effort to make it work everywhere. Furthermore, each protocol is also offering a lot of options. So it's not a simple protocol, but we can encode some of those fields in different resolutions, etc., etc. So I call that several dialects of the language. And that means if you're testing your receiver against one correction data service today, and later on the correction data service is updated, maybe your receiver is experiencing some hiccups. Or you may want to swap your correction data service provider during the lifetime of a car, which can be easily 20 years. Then you need to make sure that your receiver is still understanding the slightly different dialect of another correction data service provider. And this is one aspect where Rohde & Schwarz can potentially help with protocol conformance testing for high accuracy Ssr standards. Here is an overview about how a protocol stack looks like for those correction data services. And I've got it separated out. On the left side, you see the over-the-top IP unicast protocol stacks. For example, RTCM in Ntrip in TCP/IP, or LPP wrapped into a supple transmitted on TCP/IP. And also a lot of proprietary protocols are working with this TCP/IP stack. And this is actually the big advantage of them. They can work over any network. However, they're just working in a unicast fashion. On the right side, you see the broadcast approaches that are transmitted from satellites, for example, the proprietary standards on geostationary satellites, but also the Galileo or QCSS high accuracy services that are broadcast within the navigation message of those systems. And then there is a pretty unique aspect of LPP. The LPP standard can also be broadcast using the LTE and 5G system information blocks. So it can be carried by cellular networks and broadcast by cellular networks, not by satellites. And we will take a look at that in a moment. Here is another overview about the capabilities of the standards. I'd like to take a deeper look at the Lpp standard, as it is the 3GPP standard for high accuracy GNSS. It's supporting OSR and Ssr. It allows a very fast convergence time because it's supporting those regional correction data. It is also supporting a low data rate. It's rather bandwidth efficient. And it can be carried top IP, but it can be also broadcast using cellular networks. Looking at the integrity functionality, as of today, it is not included into LPP, but this is planned for release 17, which is scheduled for 2022. Integrity is important for life critical applications like autonomous driving, for example. And it's important to keep in mind that Lpp is driven by the 3GPP, which is also responsible for standardizing LTE and 5G in general. And every company can potentially contribute to that 3GPP standard if they would like to improve one or the other aspect. Now, I was talking about unicast and broadcast many times. What are the merits or the advantages and disadvantages of them? Unicast is top IP. That means it works on any 4G, 5G, potentially even a 3G network with any modem. You don't need any special hardware to get this unicast working. It supports also OSR and Ssr, so you can do pretty much everything with it. However, the data rate needs to be reserved for every user. If I have 10 users, I have got to transmit the same data 10 times with 1 million user 1 million times. And this makes unicast at some point becoming more and more inefficient. In the beginning, it's rather low data rate. It's comparable to a VoLTE call per user. But if we have more and more users using that, it adds up, and we can get a considerable network load using only unicast correction data. And this is actually where broadcast is coming in, and why 3GPP defined also a broadcast mode for correction data. The broadcast mode requires, however, special network support, so the base station needs to support it, and your modem needs to support it. And this is kind of the big challenge of broadcasting mode. However, if it's rolled out, then you benefit from the fact that it's scaling perfectly. It doesn't matter how many users are using it. This is not creating any additional load on the network. In the following few slides, I still want to summarize the broadcasting mode in LPP, because this is some unique aspect of LPP, and let's take a deeper look at that. How does it work? So every LTE and NR network is actually already broadcasting some data. And I'm not talking about eMBMS or this video broadcasting, but just general network parameters. For example, the neighbor cells, the attached parameters. That information is already broadcast today by every LTE and 5G network in the so-called System Information Blocks, the SIBs. And what is new in Release 15 and Release 16 is that special system information blocks were defined, the so-called POS-SIBs, and they can carry the LPP correction data within. And unlike regular system information blocks, the POS-SIBs can also be encrypted, which is a rather unique feature. So encryption, of course, is important if a network operator wants to make this a subscription model, but it's also important for the user, because a user can actually rely on that encrypted data. It's not easy to spoof such an encrypted data because the spoofer doesn't know the key, obviously. You can also create different classes of service levels. For example, a super high-end service where you have high accuracy, fast convergence, and integrity parameters for the high-end car application, and maybe another low-cost application where you're just providing high accuracy but not with a fast convergence time. So this is possible with a tiered encryption level in this POS-SIBs. How are the keys distributed in POS-SIB broadcasting? They can be distributed either in the attach message. In the attach accept, the network can tell the user this is the key for the POS-SIBs, or those are the keys for the POS-SIBs, or it can send the keys in a tracking area update. That means we can also rotate the key over time for security reasons. Please keep in mind that encryption is an optional feature. You can encrypt, but you don't have to. And if you're encrypting, of course, you need a bidirectional communication with the network. Your modem needs to talk to the network to get the keys. But if you're broadcasting them unencrypted, you can even build a receive-only device that is using that correction data from cellular networks. As a last aspect, I would like to point out that RTK and OSR is even possible with the cellular broadcasting mode. In many publications, you read that broadcasting and RTK don't go together. But this is true only if you're having a country-wide broadcast or a continent-wide broadcast from a satellite, for example. But the cellular broadcast has the benefit that we can broadcast different data in small regions. For example, in the west part of Munich, we can send different correction data than in central Munich. And that means we could even broadcast OSR correction data with this POS-SIBs. Well, that's it about the high accuracy GNSS basics and the correction data protocols. Now, thank you for your attention. I would like to hand over to my colleague Adrian.
My name is Adrian Cardalda, and I will continue this webinar. On the first part, we had a look at high accuracy GNSS and how is it working. Now, on the second part, we will have a look at why is it needed. Why do we need high accuracy positioning and GNSS? What's the market outlook and the requirements for it? During Release 15, which was the first 5G NR release, the 3GPP had a look at the 5G ecosystem and the new use cases for positioning. They identified two types of requirements, the commercial requirements and the regulatory requirements. The regulatory requirements are more relaxed than the commercial requirements, and hence we did not consider them in this overview. So we're just looking here at the most stringent use cases. For commercial, they differentiated between indoor and outdoor applications. For indoor applications, there is a requirement of under 3 meters for horizontal and for vertical positioning accuracy, and this needs to be met by 80% of the devices. For outdoor positioning, the horizontal positioning accuracy is relaxed. It's not 3 meters, it's just 10 meters. The end-to-end latency of the system is 1 second. Now, when 3GPP was discussing these positioning requirements in Release 15, they had to reach a compromise. between what was possible within the release 15 timeframe and what the market was asked for. The market was asking for centimeter level positioning accuracy. Maybe not for all applications, but the most demanding applications, they needed this accuracy. But it was not possible during the release 15 timeframe with the techniques that they had available at the moment. That's why the 3GPP continued studying in parallel, and in release 17, in the TR 38857, they came up with a new set of requirements for addressing the high accuracy applications. They divided these requirements between commercial requirements, as in the previous release, and a new sector, which is the industrial IoT business. For commercial requirements, the main difference with release 17 is the reduction of the horizontal accuracy limit from 3 meters to 1 meter, and now for 90% of the devices. The vertical accuracy stayed at 3 meters because this is sufficient to determine in which floor of the building the device is located, and this is sufficient for most of the applications already. For industrial IoT, the horizontal positioning requirement is even more demanding. It's just 20 centimeters, and we will see later why is it like that. The end-to-end latency of the system is now reduced from 1 second to 100 milliseconds only. Let us have a look at the use cases for high accuracy positioning. In release 15, the 5G ecosystem was new, and they had a plethora of new applications that was coming, like augmented reality, bike sharing, e-health, waste management, advertisement. All of these applications benefit from positioning, but for most of them, the requirements in release 15 are sufficient. They do not need more accuracy than that. For release 17, the 3GPP identified 3 sectors that have a need for higher accuracy positioning, and they categorized them as the automotive sector, the rail transportation sector, and the industrial IoT business. The need for high accuracy positioning in the automotive sector comes mainly from autonomous driving and also from collision avoidance systems. In this case, the positioning service will not rely only on 5G and on GNSS, but it will also use other sensors in the car, in sensor fusion algorithms like the radar, the lidar, and whatever is available. Nonetheless, this is a very challenging environment. To give an example, the distance between parallel tracks in a railway is just under 2 meters. So that's why this high accuracy positioning is needed for automotive. The rail sector shares some similarities, but it's also a bit different. First of all, the trains are constrained to be on the tracks, so the map can already help you in the positioning. You know more or less where the train needs to be located. Nonetheless, you have a requirement for absolute positioning. For track identification, especially in railway stations with maybe 8 or 10 parallel tracks, this requirement remains a major challenge, and also for train warning system for collision avoidance. Finally, the industrial IoT business is something completely new, and it's a little bit more diverse. Here, the positioning requirements focused on the automated guided vehicles, or AGVs, that can be used in warehouses to locate and transport the cargo. In the warehouses, you could have very narrow corridor ways where the device, the AGV, needs to access in order to locate the cargo, and therefore, the high accuracy requirement of 20 centimeters in horizontal accuracy is needed to be able to navigate through this highway, to these passageways. Now that we've looked at the use cases and the market outlook, we will take a closer look at the testing requirements. Traditionally, we had the GNSS receiver tests, which were conducted in the conducted test environment. This was the focus of our first webinar of the series a few months back. So as example, we have the test cases from TS 37571, the nominal accuracy, multipath, dynamic range, etc. These tests are sufficient to ensure the traditional positioning accuracy, because the other components of the system, of course, they have an influence on the final result, but for traditional positioning accuracy, the GNSS receiver is the main driver. Here we're talking about centimeter level. For that, we also need to take a look at the antenna, as we will see later. For antenna testing, we have the classical passive antenna testing test cases in an anechoic chamber. And there we can calculate the radiation pattern, the phase center offset, the phase center variation, etc. But that is not sufficient if we want to reach centimeter level accuracy. We also need to test how the GNSS receiver the antenna, the amplifier, and all the components in the receiver chain interact with each other. Therefore, we have the complete receiver tests. These tests evaluate the complete system performance, and they are defined by organizations such as the 5G Automotive Association or the 5GAA, and include test cases as the GNSS receiver performance pattern and sensitivity offset that we will see later on in this presentation. The key message here is that everything counts when we're trying to reach centimeter level accuracy. Malfunction in one of the components on the receiver chain could have a devastating effect on the positioning accuracy. Let us take a look at why the antenna is so important for high accuracy positioning. Before we can answer to that, we will take a look at 3 different scenarios that are typical in GNSS. Let us start with low elevation satellites. High elevation satellites, as you see in the picture, are coming from the zenith or from locations around the zenith. In that sense, the signal from the satellite crosses the atmosphere perpendicularly. As my colleague told you before, the atmosphere, especially the ionosphere and the troposphere, can disturb the GNSS signal, affecting the propagation delay and in general the GNSS accuracy. High elevation satellites cross the atmosphere following the shortest path, and therefore they are affected by the less atmospheric effect. On the other hand, low elevation satellites cross the atmosphere transversally, so they are affected by a much larger atmospheric effect. If you take a look at the picture, you will see that the signal coming from the high elevation satellite cross the atmosphere in a much smaller chunk than the signal coming from the low elevation satellite. Most of the receivers nowadays can filter out these low elevation satellites, and they do not use them in the constellation. So they take this information from the satellite orbit and they remove these satellites, not to disturb the positioning fix. The second effect that we want to take a look is multipath. So the NFS receivers typically receive the signal from the line of sight components of the satellites. But they also receive signals from the multipath components, which come from reflection on the ground, nearby objects, diffraction, atmospheric effects, etc. A large portion of these multipath components originate at the ground level, and therefore they come from a low elevation angle with respect to the GNSS receiver. Of course, not all of the multipath components come from low elevation angle, but quite some majority of them. Also, low elevation satellites are typically more affected by multipath than high elevation satellites. The last example that we want to consider are the interferences. Whether these are unintended interferences like interference from other communication systems, LTE, 5G due to harmonics, or intermodulation products, or intended interference, malicious interference coming from spoofing or jamming of the GNSS signal. Whether the interference is malicious or not, they also share in common with multipath that they come from a low elevation typically, so the interference originates at the ground level. Now that we have seen these 3 examples, we can already get an idea how a good antenna can help in reducing the error sources for GNSS. A good antenna design can help you filtering out components coming from low elevation angles, and in this sense it will help you reduce multipath and interference. At the same time, you will also filter out the low elevation satellites, but this is not a problem because most of the receivers are anyway discarding the signal nowadays, so you are not losing any valid signal. A bad antenna design, on the other side, that could have some side lobes at the horizon on the radiation pattern could even amplify this multipath effect and interference and damage the performance of the GNSS positioning system. That's why a typical good antenna for high accuracy GNSS will have a radiation pattern as shown in this slide. The area around the zenith should be designed for maximum gain in order to amplify all the desired signals. The area around and below the horizon is designed for suppression in order to filter out the undesired interference, the low elevation satellites, which is not a problem because they will be discarded by the receiver, and the multipath. This antenna pattern is very similar to what's recommended by the industry, as for instance in the 5GAA test report on vehicular antenna test methodology, which was published in June this year. We had a look at how the gain of the radiation pattern will impact on the positioning accuracy for GNSS. But what about the phase? As my colleague told you before, high accuracy GNSS methods rely heavily on phase measurements. Therefore, the phase pattern of the antenna will also play a very deterministic role in how accurate the GNSS positioning is. Let us have a look at the antenna on the picture. So let's say we have an antenna with a reference point, which is represented by the yellow dot. And this is the reference point that is considered by the positioning algorithm. After measuring the antenna pattern, we can determine the center of phases of the antenna, which is also the perceived reference point for all the signals incoming to the antenna, and is represented here by the red dot. The difference between the perceived reference point and the physical reference point is called the phase center offset. The phase center offset is a constant value for a single frequency. Once we have determined the phase center offset, we can draw the ideal uniform phase pattern around it. In reality, the phase pattern will not be ideal and uniform as this. It will be something more like this curve here, the real phase pattern. The difference between the real phase pattern and the ideal phase pattern for a given direction is called the phase center variation. This is not a constant value, it has a directional component, so it will depend on the angle of arrival of the GNSS signal. The phase center offset and the phase center variation can be calculated from the radiation pattern measurements, and they can then be modeled in order to eliminate their effect in the positioning accuracy. This is typically done in the passive antenna testing. Finally, we will take a look at the complete receiver test that evaluates the whole system performance. For this test, we will not only take the antenna or the GNSS receiver as standalone components, but we will take them together and place them in the anechoic chamber. With a satellite signal simulator, we will generate the GNSS signal, and then we will perform the test. These tests are defined, for instance, in the 5G IAA Vehicular Antenna Test Methodology report, which is linked here in this slide. The first step is to do a GNSS pattern measurement. So the test system will perform a 3D scan of the GNSS signal, and it will collect the CNO measurement reports from the GNSS receiver. This will result in the 3D CNO pattern for GNSS. The second step is to find out the beam peak of this GNSS pattern, and at that point we will execute a sensitivity offset test. For that, we will decrease gradually the power of the GNSS signal until the receiver is no longer able to calculate a fix. This will be the sensitivity level of the receiver at the beam peak. With this sensitivity level, we can offset the CNO pattern in order to obtain the GNSS sensitivity pattern. With these two tests, we have evaluated the complete system performance of the GNSS receiver, the antenna, the amplifier, and all the other components in the receiver chain. And we can certify whether our GNSS system is suitable for high accuracy or not. Now I will hand over to my colleague Stefan, who will discuss about the test solutions from Rohde & Schwarz.
Thank you very much, Adrian, for your insights into the use cases and the testing of antenna patterns for high accuracy GNSS. Now, I would like to present you a quick overview about the portfolio from Rohde & Schwarz on high accuracy GNSS test equipment. Let me start with the SMBV100B, which is a vector signal generator, and the GNSS emulator. It supports one RF, but it can simultaneously generate L1, L2, L5 signals for all the global constellations, including the regional ones. The bigger brother of the SMBV100B is the SMW200A. It can come with two RF channels and can therefore be used for receivers that feature multiple antennas, for example, in an automotive environment where you want to use multiple antennas to determine your heading. It can also be used for interference emulation, and it can be also extended to more than two RFs with external add-on devices. Both those GNSS simulators can also be used to generate correction data streams. Furthermore, we also offer network emulators for 2G, 3G, 4G, and 5G. For the older radio access technologies until 4G, this is the CMW500, and the CMX500 covers also 5G. That can be used to also bring the correction data streams over the air into the device, for example, if you do not have access ports to your device to inject the correction data streams. Finally, RNS is also offering the WPTC shielded room, which can be used for this PCO, PCV, and gain pattern measurements that Adrian was mentioning before. This comes with a vector network analyzer and a signal generator that can be used to determine the PCO, PCV, and other parameters with the highest accuracies. Well, with that, I would like to conclude the webinar. We've presented you, Adrian and me, today the basics of high accuracy GNSS, how correction data can be transported to the devices, which types of correction data are used, the use cases of high accuracy GNSS in an automotive and industrial and railway environment, and many more. And last but not least, also the impact of antenna patterns and the antenna testing capabilities that we are offering for high accuracy GNSS. On behalf of my colleague Adrian and me, we'd like to thank you for your attention, and we're looking forward to see you in the next webinar. Thank you very much.
예, 지금까지 준비된 동영상 내용을 쭉 보셨습니다. 그래서 현재 이제 앞으로 이야기할 고정밀 GNSS에 대해서 뭐 여러 가지 프로토콜적인 알고리즘이라고도 보통 표현을 하죠. 이런 부분들에 대해서도 말씀을 드렸고요. 그리고 이제 마무리는 실제 이동통신 관련한 기술적인 부분으로서 어떤 측정 솔루션에 대한 부분까지 이제 말씀을 드렸습니다. 예. 지금 뭐 쭉 내용 한 40분 정도 저희 동영상 같이 보셨는데요. 먼저 한번 간단하게 전체적인 요약 한번 부탁드릴 수 있을까요?
예, 알겠습니다. 일단 앞서 저희가 말씀드렸던 부분들이 많이 지금 소리가 안 좋았다고 해서 요약을 해드리자면, 오늘 있었던 내용들은 지금 주로 주요 주제는 LBS의 확장 부분입니다. 그래서 예전부터 있었던 위성 기반의 로케이션 베이스드 서비스에서 이제 확장돼서 기지국이 도울 수 있는 부분들, 뭐 GNS에서 AGNSS라는 부분까지 확장이 됐었고, 최근 릴 15에서 5G 릴 17까지 확장되면서 OSR, SSR 기반의 RTK-PPP 그리고 RTK-PPP 이 부분에 대해서 저희가 설명을 해드렸고요. 그 세미나 자료에서 있었던 부분들은 사실 전체적인 로케이션 베이스드 서비스에서는 굉장히 일부에 대한 부분이고요. 테스트 항목 중에서도 극히 하나의 분야일 뿐입니다. 그래서 더 자세한 부분들은 저희 쪽으로 이제 많이 메일이나 전화로 문의를 주시면 추가로 설명을 해드릴 수 있고, 추가적인 솔루션도 설명을 해드릴 수 있을 것 같습니다.
예, 뭐 서머리에 덧붙여서 또 같이 말씀을 드리면, 이제 LBS라고 하는 부분이 뭐 사실 저도 처음엔 그랬습니다만은 이제 위치 기반 서비스 이 부분이 이제 GPS라고 불리는 이 위성 신호만을 이용한다라고 생각을 했었는데, 지금 현재는 뭐 이미 이동통신 기술과 결합이 되어 있는 뭐 스마트폰에서 이미 우리가 다 위치 측위를 하고 있으니까요. 이런 식으로 사용이 되고 있고, 그리고 또 아까도 말씀해 주셨던, 오늘 뭐 동영상에서 나오진 않았습니다만은 수직적인 위치까지도 우리가 다 파악할 수 있다. 그리고 뭐 블루투스나 이런 와이파이와 같은 기술들과도 현재 결합이 되고 있기 때문에 뭐 비콘이라든지 이런 부분들을 또 얘기를 할 수 있다. 뭐 이런 부분들 이제 간단하게 말씀을 드렸었고요. 오늘 주제 GNSS, 뭐 솔직히 처음 제가 생각했었을 때는 GNSS라고 하는 부분들이 정말 그렇게까지 복잡한 건 아닐 것 같다, 이제 이런 생각도 했었는데, 실제 내용을 쭉 들어보면은 사실 그 이상의 내용들이 있는 것 같아 보여서 이 분야도 또 상당히 어떤 기술적으로도 그렇고 서비스 측면에서도 그렇고 또 잠재성이 굉장히 큰 그런 부분이 아닐까, 뭐 이런 생각이 들기도 하네요. 예, 그래서 지금 뭐 5G 쪽 얘기를 뭐 연관성을 좀 보자면은, 특히 뭐 이런 부분들은 우리 최근에 얘기 나오는 부분들이 뭐 차량 간 통신이라든지 이런 쪽에서도 이제 또 이런 GNSS나 위치 측위에 대한 부분들을 활용을 할 계획들이 있는 거잖아요. 그렇죠?
네, 맞습니다.
예. 뭐 저도 뭐 이런 아름아름에서 들은 내용들을 보면은, 특히 뭐 CVTX, 뭐 차량 간 통신 같은 개념을 놓고 이야기할 때에는 우리 뭐 기존의 GPS에서 상상하지 못했던 그런 어떤 정확도를 가지고, 뭐 심지어는 뭐 얘기를 들어보면은 차선에 대한 구분을 기준으로 하고 있다, 뭐 이런 얘기도 나오더라고요.
네.
예, 그래서 그 정확도라고 하면은 계속 이동통신 기술이 발전하는 만큼 또 함께 결합이 돼서 발전을 하고 있는 게 아닌가, 뭐 이런 생각이 들기도 합니다. 예, 그래서 진행되는 동안에 이제 질문을 굉장히 많이 올려주셨어요. 그래서 그 부분도 이제 뭐 저희가 시간 뭐 허용되는 만큼 또 말씀을 드려야 될 것 같습니다. 그래서 먼저 그 정영규님께서 이제 질문을 주셨는데, 정영규님은 질문 몇 가지 같이 주셨어요. 그래서 첫 번째 질문이 그 GNSS, GPS 위치 측정과 통신사업자 기지국 위치로 찾는 것 서로 오차가 얼마나 있느냐 뭐 이런 거를 물어봐 주셨네요. 혹시 뭐 답변을 좀 해주실 수 있을까요?
사실 이 부분은 정확하게 답변 드리기는 좀 어렵습니다. 그냥 이론적으로, 그리고 저희가 테스트하면서 아름아름 아는 부분들에 대해서 알려드리자면, 예전에 위성만 사용해서 GPS 측정을 하는 경우는 약 기본적으로는 50m, 그리고 조금 정확도를 높인 경우에 플러스 마이너스 10m, 20m 내외 반경에서 오차를 허용한다. 이 정도로 위성만 사용했을 때 그렇게 됐었는데, 통신사업자가 이제 기지국을 사용해서 위치를 좁히는 방법에는 여러 가지가 있습니다. 예를 들어서 뭐 AOA 방식도 있을 거고, 혹은 TDOA, 타임 디퍼런스를 이용한 기지국 간의 시간차를 이용해서 오차를 줄이는 방법도 있을 겁니다. 그리고 지금 말씀드리는 기술들 하나하나가 다 개별적으로만 사용되는 게 아니라 결합돼서도 사용이 되고 있어요. 그래서 뭐 예를 들면 아까 초반에 말씀드렸던 3점치기 이런 부분이 위성만 3개를 사용하는 게 아니라 위성 하나에 기지국 2개, 또는 위성 2개에 기지국 하나, 이런 식으로도 결합돼서 사용되기 때문에 그 오차가 얼마나 줄어드냐라고 말씀드리긴 어렵습니다. 단 지금 릴 17에서 목표로 하고 있는 오차 레벨은 센티미터 레벨입니다. 그래서 1m 이내를 센티미터 레벨로 보고요. 뭐 99cm도 센티미터 레벨이니까요. 그래서 1m 이내의 오차로 목표로 삼고 5G에서 6G 넘어가는 지금 길목에서 LBS 기술의 목표로 삼고 있는 것 같습니다.
예, 지금 말씀해 주신 내용 중에서 제가 또 좀 재밌는 이야기 같아 보여서 이제 생각이 나는 부분이, 실제 우리가 흔히 얘기하던 이 GPS, 위성을 이야기하고 할 때 이 위치 측위에 대한 부분하고, 또 그 이동통신 기지국을 이용을 할 때 이 위치 측위 기술 부분은 이게 서로 같이 연관돼 있다라면 사실 근본적으로는 서로 다른 별개의 기술인 거잖아요.
네, 맞습니다.
예. 근데 다만 지금 오늘 동영상에서 나온 것처럼 이런 어떤 내용들 서로 보강을 해주기 위해서 그 이동통신 기술의 어떤 시스템 인포메이션에서 기지국 신호에 대한 내용들을 보조적으로 이제 같이 브로드캐스팅 해준다라든지 이런 식의 어떤 서로 도와주는 개념들이 지금 서로 결합이 되어 있는 거지, 근본적으로 이게 서로 다른 기술이다 뭐 이런 부분들이 맞는 이야기겠죠?
네, 사실 지금 말씀하신 부분이 순차적으로 보면 원래는 위성 신호만 사용하는 방법을 예전엔 GPS 혹은 GNSS라고 불렀고요. 거기에서 우리가 위치를 잡기 위해 필요한 데이터를 위성으로부터 다운받는 게 시간이 오래 걸리고, 예전에 뭐 내비게이션의 1세대 초창기에는 켰을 때 부팅하고도 위치를 찾는데 오래 걸렸잖아요. 그런 부분들을 보완해주기 위해서 그 어시스티드 GNSS, AGNSS라고 불리는 부분이 AGPS, AGNSS라고 불렸던 부분이고, 그거와 별개로 이제 LTE 기지국에서는 기지국 자체에서 제공하는 정보가 3G에 비해서 훨씬 많아졌습니다. 그래서 기지국 정보 안에 셀 아이디라든지 위치에 대한 정보들이 같이 프로토콜 메시지로 내려가게 됐고, 그것만을 이용해서도 위치를 측이할 수 있는 기술들이 LTE에서 독자적으로 나와서 OTDOA, UTDOA 혹은 ECID 이런 기술들이 나왔고요. 하지만 기술과 기술 자체를 계속 분리해서 발전시키면 결국은 원하는 바를 이루기가 좀 어렵잖아요. 그 두 개를 같이 결합하는 게 이제 하이브리드 메소드입니다. 그래서 하이브리드 메소드는 LTE 때부터 소개가 됐고, 5G 때도 뭐 여러 가지 기술들, 위성 신호와 기지국을 계속 결합하는 내용들이 추가가 되고 있고, 이뿐만 아니라 기지국뿐 아니라 앞서 말씀드렸던 와이파이 AP, 블루투스 비콘 이런 부분들에 포함되는 인도어 포지셔닝 이런 것도 같이 하이브리드 메소드로 다 섞여서 측정하고 단말이나 칩셋에 요구되는 사항으로 추가가 되고 있는 겁니다.
그렇다면은 실제 시험이라는 관점에서 본다고 할 경우에도 결과적으로는 GPS 자체에 대한 뭐 예를 들면 GPS 칩에서 어느 정도로 이 위성 신호들을 파악을 할 수 있느냐도 중요하겠지만 실제 어떤 예를 들자면 스마트폰이나 이런 단말에서 이동통신 기지국에서 어떤 신호를 제대로 받는 거냐, 제대로 디코딩을 하는 거냐, 이런 이야기도 실제로 어떤 시험의 항목이나 범위에 포함을 시켜야만 될 수 있다, 뭐 이런 개념이 될 수가 있겠네요.
네, 당연히 기지국 시그널링에 대한 부분도 시험 항목에서 포함이 되는 부분이고요. 그래서 LTE를 예로 들면 저희는 LTE의 RF 시험을 LBS RF 테스트라고 불렀고 LBS 프로토콜 테스트는 따로 분리해서 LPP라고 불렀습니다. 그래서 LTE 포지셔닝 프로토콜이라는 개념으로 새로운 이름을 붙이고 LPP 테스트를 했습니다. 근데 5G에 와서는 특이하게 뭐 5G 포지셔닝 프로토콜이라는 이름을 만들진 않았고 그대로 LPP라는 용어를 그대로 사용하고 있는 상황이고요. 그래서 LBS 테스트라고 하면 RF적인 측면, 프로토콜적인 측면 모두를 다 확인해야 되는 부분입니다.
알겠습니다. 예, 다음 그 질문을 볼게요. 저 김형구님께서 질문을 주셨네요. 그 오차에 대한 부분인데요. 고층 건물이 많을 경우에 RTK 정확성을 높일 수 있는 방법이 있을까요?
사실 지금 테스트 방법 자체는 RTK만 보고 하면은 안 될 것 같아요. 왜냐하면 오늘 세션 자체가 세션 초반에 이제 질문을 주신 부분인데 RTK라는 방식이 있고 PPP라는 방식이 있고 그 두 개를 서로 같이 합쳐서 RTK-PPP라는 방법을 통해서 정확도 그리고 컨버전스 타임을 줄이는 방식으로 소개가 됐습니다. 그리고 지금 건물이 많은 곳에서의 정확성을 높이는 방법에는 다른 부분으로 설명드렸던 많은 기술들이 있을 거예요. 뭐 바로메트릭 센서도 있을 거고 다른 인도어 포지셔닝에 대한 부분들이 이미 저희 휴대폰 단말에는 많이 들어가 있습니다. 그래서 안드로이드 폰을 예로 들면 로케이션 메뉴, 그러니까 위치치기 메뉴에서 이 기본적인 위치 정확도, 높은 정확도, 더 높은 정확도 이렇게 세 단계로 이제 설정을 할 수 있게 돼 있거든요. 그런 부분들은 이제 구글에서 제공하는 LBS 서비스에 사용되는 앱의 확장성을 포함하는 내용이죠. 그래서 네, 그 정도로 줄이면 될 것 같습니다.
예, 뭐 바로미터, 뭐 기압 센서 이런 부분들 말씀해 주셔서 바로 위에 있는 질문도 이어서 말씀드릴 수 있을 것 같은데, 뭐 이런 부분들은 뭐 기압 센서나 고도 센서 같은 경우에는 특히 뭐 제 생각으로는 아웃도어에서 좀 더 유용할 것 같긴 한데,
네.
뭐 없다면은 건물 내 몇 층에 있는지 알 수는 없는 건가요? 뭐 이런 경우에는 방금 얘기해 주신 것처럼 비콘이라든지
네.
뭐 이런 부분들이 또 보조적으로 등장할 수 있는 부분이기 때문에 이런 부분들은 뭐 여러 가지 조합을 해서 썼을 때 더 정확한 어떤 위치 측일을 할 수 있는 그런 개념이 아닐까 싶기도 하고요. 조금 더 위로 올라가 볼까요? 뭐 지금 시간 관계상 모든 질문에 답변 드리기는 좀 쉽진 않을 것 같고요. 예, 여기 저 문주웅님께서 물어봐 주셨는데요. OSR과 SSR 코렉션 데이터의 유사점, 차이점에 대해서 문의를 주셨네요.
네, 이 부분은 사실 아래쪽에 있는 다른 좋은 질문들도 많았습니다. 근데 이 코렉션 데이터의 유사점과 차이점 이 부분을 같이 찝은 이유는 내용 자체를 제가 바로 현장에서 설명드리는 것보다는 메일로 자료와 함께 답변 드리는 게 더 좋을 것 같은 부분이 있어서 찍었고, OSR과 SSR 코렉션 데이터의 차이점은 사실 질문한 시점 이후에 슬라이드에서 나오긴 했습니다. 그래서 서로의 프레임 구조가 좀 다른 상황으로 돼 있고요. 그 다른 부분에서의 유사점이라고 하면 결국은 위치 정보를 얼만큼 포함하고 있냐가 되겠죠. 그런 부분들이 유사하고 차이가 나는 부분인데 그 프레임 구조나 그런 부분에 대해서는 추가로 이메일로 답변을 드리겠습니다.
네. 그래서 저희 쪽에서 한 번 더 뭐 이메일을 통해서 좀 자세한 내용들을 말씀을 드릴 수 있을 것 같고요. 제가 먼저 말씀드렸어야 되는데 좀 깜빡 좀 그 말씀 못 드린 부분이 있습니다. 그 오늘 진행된 그 웨비나 동영상은 저희 이 토크IT에서도 다시 보기를 하실 수 있고요. 또 저희 로데슈바르즈코리아 홈페이지를 통해서 여러분께서 그 다시 보기 및 자료 다운로드도 저희가 제공을 해드릴 겁니다. 이건 뭐 저희 내부적으로 그 준비를 하는 과정에서 약간 시간이 걸릴 수 있기 때문에 추후에 저희 쪽에서 참석자분들께는 관련된 내용으로 따로 인폼을 드릴 수 있을 것 같아요. 그래서 이 부분을 참조를 해주시면 좋을 것 같고요. 예, 원래 예정된 시간이 저희 5시까지로 준비를 했었는데 뭐 아까 그 혼선 문제도 있었고 해서 조금 더 이야기를 하다 보니까 좀 시간이 길어졌습니다. 뭐 시간상으로는 뭐 질문 하나 정도 더 답변을 드리고 오늘 이 정도로 정리를 해야 될 것 같은데요. 바로 위에 저 조민성님께서 질문을 해주셨어요. 와이파이나 비콘 등 사업자 동의가 있어야 활용 가능할 것 같다고 하셨는데요. 이런 부분에서 이제 가능한 측면과 가능한 방안, 그리고 사업자 간 협약에 대한 어떤 현재 단계, 뭐 이런 부분들을 지금 포괄적으로 질문을 해주셨습니다. 어떻게 좀 말씀을 해주실까요?
이 부분은 사실 기술 자체가 열려 있는 상황이기 때문에 사업자가 활용할 수 있는 방안도 충분히 있고요. 사업자가 활용하지 않고 퍼블릭으로 사용할 수 있는 부분도 있다고 말씀드릴 수 있습니다. 예를 들면 기존의 LTE 기술에서 와이파이 부스터 같은 경우는 와이파이를 이용해서 다운로드 속도를 늘리는 건데, 그런 경우에는 뭐 SKT나 KT 사업자별로 각자의 AP를 각자의 가입자들한테만 제공을 했었죠. 이런 경우는 사업자 AP에 묶여서 서비스가 제공된다라고 볼 수 있는데, 반대로 뭐 공공적인 박물관이나 아니면 공공장소에 있는 비콘들은 우리가 제한 없이 사용할 수 있잖아요. 이런 부분들에 대해서는 사업자가 관여할 수 있는 부분이 없습니다. 그래서 기술은 테스트 측면에서, 그리고 단말 제조사 입장에서는 사용할 수 있는 기술에 대한 제약을 없이 다 개발을 해서 기능들을 넣어두는 거고요. 그 어플리케이션들은 각각의 장소에서 그리고 각각의 위치에 맞게 활용될 수 있다고만 말씀드리면 좋을 것 같습니다.
뭐 결국은 기술 자체는 오픈되어 있지만
네네.
이걸 이용해서 어떤 사업을 할 거냐, 비즈니스 모델은 또 그것과는 별개의 이야기가 된다.
네,
뭐 이렇게
맞습니다.
생각해도 되겠네요. 예, 알겠습니다. 예, 뭐 오늘 질문 굉장히 많이 주시는데, 뭐 아까도 말씀드린 것처럼 죄송합니다만은 시간 관계상 모든 질문을 저희가 이 자리에서 답변 드리기 좀 쉽진 않을 것 같습니다. 그래서 일단 시간이 벌써 5시 6분, 7분이 돼가고 있는데요. 이 정도에서 오늘은 정리를 하고, 그 질문 주신 분들께는 저희가 추후에 그 이메일을 통해서 다 따로따로 개별적으로 답변을 준비를 해서 따로 말씀을 드려야 될 것 같습니다. 일단 오늘 저희 준비한 내용은 여기까지이고요. 마지막으로
네.
인사 한번 해주시죠.
예, 오늘 제가 이 토크 IT에서 하는 웨비나는 처음이고요. 저희 로데슈바르즈코리아에서 진행하는 오프라인 세미나는 예전에도 몇 번 해서 저를 뵀던 분들이 좀 있을 것 같은데, 아무튼 어색하게 답변하고 좀 긴장한 모습을 보여서 죄송합니다. 그리고 감사합니다.
예. 그래서 이제 또 다음 주에는 또 구정이잖아요. 그래서 오늘 참석하신 모든 분들 즐거운 구정 명절 보내시고, 또 음력이긴 합니다만 또 새로운 새해 또 새 마음으로 또 좋은 일들 가득하시길 다시 한번 빌겠습니다. 오늘 저희 내용은 여기서 정리하도록 하겠습니다. 수고하셨습니다.